the first thing I would like to show you in the transmission line analysis model is basically the lossless case, because that's by far the simplest. And once we understand the lossless case, then we'll go ahead and look at our lossy case scenario. So in a lossless case, I got rid of my resistance and conductance, and I'm only left with the inductance per unit length, which you can see here, and the capacitance per unit length as the main unit cell of the transmission line. Now, of course, in an ideal transmission line, you don't have a single unit cell, but ideally you have an infinite cascade of those that essentially makes the transmission line model. So let's see how we're going to analyze this. So we're going to assume that we have some type of a voltage on the left-hand side, which I have called here V of z. And that means that right at the end of that unit cell, I will have a different voltage, which is V of z plus delta z. And similarly, I will have some type of current that enters the unit cell, I of z, and some type of current that exits the unit cell, I of z plus delta z. So my main goal in the next couple of slides is to actually link those two. So link this current that you will see here, and link the voltage that you will see here through a couple of equations. It's actually relatively easy to do that. So let's go ahead and do this for the voltage case. So if I just consider my unit cell that you will see right here, all I have to do is basically apply Kirchhoff's voltage law. And so you will basically find out that the V of z that you have on the left-hand side minus the voltage drop that you will get across the inductor will basically give you the V on the right-hand side. And it's literally as simple as that. So just by applying Kirchhoff's voltage law here, you will have this first equation, which yields this equation here. And once you let delta z to go to 0, since ideally we have a 0 length unit cell, you will basically get the equation I have in this blue box as my first differential equation that links the derivative of my voltage to the current. And I'm sure that you have already noticed that, but there is no time here. So these are not time domain equations. These are basically phasors. I'm not going to be putting phasors here for the rest of the class, but I do want to emphasize here that this is phasors. And second, this is a function of z, not time. So that means that all of these quantities is a function of length of the transmission line. Also, I'm assuming that I'm doing this analysis right now at a single frequency. This is the frequency of interest. And I will also assume, as is the case for the ideal transmission line, that this L and this Z are independent of Z. So they're not a function of Z, and they're not a function of Z. In other words, I'm assuming that the transmission line cross-section is actually independent of distance. Inductance per unit length and capacitance per unit length are basically constant. So that's my first equation under these assumptions. And the second equation actually is very similar. Now I will go ahead and apply my Kirchhoff's current law right at this node here. So the current that comes from my left-hand side minus the current that will basically go through the capacitance will be equal to the current that will continue to the right-hand side. So a simple KCL now will essentially give me, at the limit of delta z going to 0, it will basically give me my second equation that now links the derivative of the current to the voltage. So this equation that I just got before, the one here for the voltage and the one here for the current, are basically two differential equations that have a very famous name, and they are called telegrapher's equations. You can imagine that those days that appear to be a few centuries ago, telegraphers were actually using these equations to understand how to send signals over, at the time, two wire lines. Now, you can take those two telegrapher's equations and decouple I and Z, I and V rather, which I won't do here, and essentially then get what's called the wave equation. So I have the math in my notes if you want to look at them. And so you will have identical wave equations for the voltage and the current, which is our first, I would say, proof that the only thing that truly exists on a transmission line are the waves. And in fact, there are two waves, one which we will call the forward wave, which is the solution of this equation, and one that is called the backward wave, which is also a solution of this equation. So the forward wave will have some type of an amplitude, which I'm calling here V0 plus, and it will have this exponential response, e to the negative j beta z, where beta is essentially the propagation constant of the transmission line. And it can be found by just solving this one-dimensional equation. So I know all of you know how to solve one-dimensional equation. If you do that, you will find that the propagation constant is equal to omega square root of LC, or 2 pi by lambda, or omega by v, where this v is my phase velocity. It's basically the propagation velocity of the wave. Similarly, the backward wave will have an amplitude of now v naught minus and a phase dependence of e to the j beta z, since this guy is propagating at the negative z direction, and this guy is propagating in the positive z direction. What exactly is v naught plus and what exactly is v naught minus? It actually depends on my boundary conditions. And boundary condition means what is your load and what's your source. So how do you excite the transmission line, and what kind of a device do you feed? And we'll actually see in the later part of this analysis how exactly we find v naught plus and v naught minus. For right now, they're just unknowns. Once I know my solution to the wave equation from a voltage perspective, I can just go ahead and find current I. And as you can probably imagine, this current I can be found very easily, for example, from the first equation. So I can plug in my voltage that you know to this equation here, and that will yield basically I. So if you do that, if you just plug into the first equation the solution for the voltage, you will get a current that is nicely written here, which is essentially almost the same thing. The only difference is that you have this Z naught, which you will see right here. It's basically a constant, is the square root of L by C. And you will also have this negative sign instead of the positive sign that you will have here, which is just a direct expression, a direct result of differentiation. So there is basically, again, a forward current wave, which has an amplitude of V naught plus by Z naught, and a backward wave that has an amplitude of V naught minus by Z naught. And this constant Z naught has a very famous name. It's called characteristic impedance. And as you can probably guess from its name, it has a value, it has a unit of ohms. So in other words, what is the characteristic impedance of a transmission line? The characteristic impedance of a transmission line is nothing else but the ratio of the voltage over a current for the forward wave, or the negative ratio of the voltage over the current for the backward wave. And it's a real number. It has a value of square root by LC, meaning inductance per unit length divided by capacitance per unit length, and it has units of ohms. And there's also another very interesting expression which we will actually use quite often, is simply 1 by CV, and this is nothing else but by utilizing that the V is 1 by square root of LC. So if you utilize that the V is 1 by the square root of LC, you will find out this equation for Z naught. So in this slide, what we basically found out is that the only governing equations that we have to know are the wave equations, which I know you've seen from your undergraduate days. You know the solution for a wave, in this case, is just one-dimensional. And there are the two explicit solutions for voltage and current.